In this lecture, we discuss some concept of sequence for B.TECH student. First, the definition. The sequence is a function f from natural number to the set of real number, where n is said to be the set of all natural numbers and R is the set of all real numbers. So this is the definition of sequence. Next, we give some example. As for example, 1 by n, such that n belongs to natural number. In this case, it will vary n equals to 1, 2, 3, 4 and so on. So we get the sequence, that is 1 by 1, 1 by 2, 1 by 3, 1 by 4 and so on. That is 1 by 2, 1 by 3, 1 by 2 and so on. This is the original sequence. Here note that n equals to 1, 2, 3, 4 and so on. So this is the first example. Next, 2n such that n belongs to natural number and sin pi by n such that n belongs to natural number. These also are the examples of sequence. Now we discuss the notation. Generally, sequence can be written as this format, or also can be written as simply xn when n belongs to natural number. These are the notations of the sequence. Next, we study bounded sequence. Bounded means which have some boundary, some lower or upper. As for example, if we draw a shape or figure which have a lower boundary and also upper boundary, and also in vertical have a upper boundary and have a lower boundary. So this is a bounded figure. But if you draw a figure whose any one end is open, then this is bounded by any upper quantity, but this is open in this portion, that is the lower portion. So in a bounded sequence there exists also some lower boundary and upper boundary, or least upper bound or greatest upper bound. So the definition is the sequence is called bounded if it is both bounded above and below. That is, for any sequence xn n equals to 1 to infinity, there exists k which is a real number such that any term of the sequence, that is xn, which is less than or equals to k for all n belongs to natural number. That is, if we open this inequality, then we get this kind of inequality. Since we know that definition of mod is class A if A greater than or equals to 0 and minus A if A less than 0. This is the definition of bounded sequence. Both this is the lower boundary and this is the upper boundary. If this kind of inequality holds in any sequence, then we say that it is bounded sequence. If only exists upper boundary, then we say that the sequence is bounded by any real number. Or if there exists only this kind of lower number minus a less than equals to xn, and there does not exist any upper boundary, then we say that it is bounded below. Next we discuss some example of bounded sequence. First example, the sequence an is defined by n equals to 1 by n square, or n belongs to natural number. This is a bounded sequence since it is a bounded sequence. Since n belongs to natural number, this means that n greater than or equals to 1. So if we square both sides, then n square greater than equals to 1. So if we invert both sides, then 1 by n square is less than equals to 1. this shows that one by n square is less than equals to 1, and also n belongs to natural number, and natural number is set 1, 2, 3, 4 and so on. So in each case natural number n greater than equals to 0. This implies that 1 by n is also greater than equals to 0. Since these are the non-zero numbers, so we divide 1 by some 1 by 1, 1 by 2, 1 by 3, 1 by 4. In each case 1 by n also greater than or equals to 0. So this inequality holds. This implies that 1 by n square also greater than equals to 0. So if you combine this inequality and this inequality, then we have 0 less than equals to 1 by n square less than equals to 1. So this kind of inequality holds in this case. So 0 is the lower bound and 1 is the upper bound. This is lower bound and this is upper bound. So the sequence is bounded by both lower and upper. So the sequence 1 by n square such that n plus natural number is bounded. Example number 2. The sequence n equals to 1 to infinity is defined by n equals to 3 to the power n minus 1. This is the sequence. Now put n equals to 1, 2, 3, 4 and so on, then we get each term. First term a1 n to the power 1 minus 1, that is e to the power 0, 1. Next a2 3 to the power 2 minus 1, 3 to the power 1 equals to 3. a3 3 to the power 3 minus 1, 3 square 9. a4 a to the power a4 3 to the power 4 minus 1, 3 to 27 and so on and so on. So the sequence looks like in this way: 1, 3, 9, 27 and so on. Here we see that these are the terms a1, a2, a3, a4. In each case is greater or equals to 1 or it belongs to natural number. So 1 is the lower bound. If we find the resistant k for which this kind of inequality is satisfied, then we say that the sequence is bounded. Here 1 is less than equals to n. Now if we get this kind of upper bound, then we only say that the sequence is bounded, otherwise not. So we find the upper bound. Now here note that in each time the number is increasing. 1 to 3 multiplied by 3 to 9 into 3, 9 to 27 into 3, and the next term is the multiplied form of the previous term. So in each case the number is bigger than the previous one. So we see that there does not exist any kind of upper bound for which this kind of inequality is satisfied. Basically, this tending to infinity. As n goes to infinity, n tending to infinity. So there does not exist any kind of upper bound. So there does not exist any upper bound. So we said the sequence is unbounded. The sequence is unbounded. So this is an example of unbounded sequence, and the previous one bounded sequence. Next we discuss the limit of the sequence. A sequence of real numbers is said to tend a limit L if there exists a epsilon which is greater than 0 and a positive integer capital N depending on epsilon such that for every n suffix n small n, for every n greater than capital N, we have the distance between an and the limit L. The distance between an means the terms of sequence and L is less than epsilon. Now notation. This also can be written as limit n tending to infinity an equals to n. This is the limit of a sequence. This question, here in this question, we find the limit of the given sequence, or rather we say that this is the given 4/3, and we show that this 4/3 is a limit of the sequence using the previous definition which we have studied earlier. Now by definition we show that n minus L less than epsilon whenever n greater than some any capital N, then we say that n is a sequence of the original sequence. So n minus L less than epsilon, that is here the sequence is is 4n plus 3 divided by 3n plus 4 minus l, and we justify that 4 by 3 is a 8. Then we put l in this expression, that is 4 by 3, which is less than epsilon. That is, if then we simplify this expression, and if we get this kind of capital N, then we say that this is a limit, otherwise not. So let's find if we get some this kind of capital N or not. So simplify this. That is if 3 into 10 plus 4, open the brackets, for the space I remove some quantity, that is E, cancel this 9 minus 16 minus 7 divided by 3 into 10 plus 1 is less than epsilon. That is E, taking mod both sides, mod of minus 7, 7, and since this is a natural number, so altogether number is positive and 3 is also positive quantity, so we get 7. That is, if 3 into 3n plus 4 divided by 7 is greater than 1 by epsilon, since you know that if quantity A is greater than B, then 1 by A is less than 1 by B, or vice versa. That is, if 3 into 10 plus 4 greater than 7 by epsilon, and taking this 3 in denominator part, so you get this. That is, if 3n is greater than 7 by 3 epsilon minus 4, that is, if n greater than 1/3 of 7 by 3 epsilon minus 4. This is the expression. Now taking capital N equals to 1/3 of 7 by 3 epsilon minus 4, where epsilon is greater than 0. So we see that this 4n plus 3 divided by 3n plus 4 minus 4 by 3 is less than epsilon whenever n greater than capital N, and capital N equals to 1/3 of 7 by 3 epsilon minus 4. So you get this kind of capital N, that is N minus L is less than epsilon whenever small n greater than capital N. So we successfully find this kind of capital N, which is 1/3 of 7 by 3 epsilon minus 4, and hence we say that by the definition of limit, we say that 4 by 3 is a limit of the original sequence 4n plus 3 divided by 3n plus 4. Now we discuss the convergent, divergent and oscillatory sequence. Convergent, divergent and oscillating sequence. We already find the limit, that is L, if n tending to infinity, An equals to L, then L is set the limit. We already discussed about it. Now if the limit L of the sequence is finite, then the sequence is convergent. L is infinite, then the sequence is divergent, and if neither L is neither finite nor infinite, then the sequence is oscillating sequence. So this is the key point. If L is finite, then the sequence is convergent. L is infinite, then the sequence is divergent, and neither convergent nor divergent, then the sequence is oscillatory sequence. I will discuss some example. Example number 1. 1 by 3, 1 by 3 square, 1 by 3 cube, and so on is convergent. It's convergent since its general term A equals to 3 to the power n minus 1. First term 1, second term 1 by 3, 3 to the power 2 minus 1. Third term 3 square, which is 3 minus 1. Fourth term 1 by 3 cube, 4 minus 1, and so on. So now if we take limit n tending to infinity, then 1 by 3 to the power n minus 1, which is also goes to infinity, 3 to the power infinity, so 1 by infinity, and this goes to 0. So which is finite. So the sequence is convergent. So this is convergent. Next, we consider An equals to 3 to the power n, and this is divergent. since if n tending to infinity, then limit 3 to the power n, 3 to the power infinity, which is goes to infinity, and this is infinite. So this is an example of divergent sequence. Next, we consider this sequence minus 1 to the power n. Now the sequence looks like, if put n equals to 1, then value is minus 1, put n equals to 2, the value is plus 1, and so on. Minus 1, plus 1, minus 1, plus 1, minus 1, continue in this fashion. So in each case we see that the terms are minus 1, plus 1, minus 1, plus 1. So it is neither converge in a particular value or not diverge. So this kind of example is an example of oscillatory sequence. Oscillating sequence. So this is an example of oscillating sequence. Result. The monotone increasing sequence which is bounded above, then the sequence is convergent and converges to its exact upper term. And result number 2, the monotone decreasing sequence which is bounded below then the sequence is convergent and converges to its exact lower bound. This is the very important result for showing a monotone increasing sequence is convergent and monotone decreasing sequence is convergent. So we stop the lecture here, and in the next lecture we discuss about some examples about it and another various concept. Thank you.